Hello everyone, and welcome. I'm excited to kick off our presentation today. We'll be exploring the Grade 4 Wastewater Operator Exam Review. This is a comprehensive study guide designed to help you prepare for your certification. We'll cover key topics like general treatment principles, activated sludge processes, trickling filters, and rotating biological contactors. Additionally, we'll look into waste treatment ponds, sludge digestion, odor control, nutrient removal, disinfection, solids management, microbiology, and chemistry fundamentals. So, in the next few slides, we'll walk through each of these important areas to give you a solid understanding. Let's get started. Let's take a closer look at some general wastewater treatment principles. First, regarding safety standards, it's important to be aware of the chlorine gas odor detection limit, which is around 0.3 parts per million. That means if you smell chlorine at that level, it's a sign that concentrations are getting close to potentially hazardous. When working in trenches that are 4 feet or deeper, we need to ensure there are exits at 25-foot intervals for safety, in case someone needs to evacuate quickly. Also, for equipment like mechanical seals, the operating temperature should never go beyond 160 degrees Fahrenheit or about 71 degrees Celsius unless the system is water-cooled. Staying within these limits helps prevent equipment failure and ensures safety. Moving on to equipment fundamentals, the cathode is the negative pole in an electrolytic cell. Understanding this helps us grasp how electrolysis works in water treatment processes. When dealing with water sources below the pump, the concept of suction lift comes into play. It's simply when the water supply is below the pump's centerline, affecting how we design the pumping system. And for controlling water hammer, needle valves are particularly effective because they allow fine regulation of flow, helping to dampen sudden pressure surges that can damage piping. Now on to chemical principles. Strong acids release more hydrogen ions than weak acids, which is key when considering pH control and chemical dosing in treatment processes. Stray current corrosion is another critical concept. It's caused by external electric currents that lead to metal decomposition, and minimizing this is vital for maintaining infrastructure longevity. Lastly, when we talk about cathodic metals, these are generally the least reactive, which is why they're often used in applications where corrosion resistance is essential. Connecting all these points, understanding safety standards, equipment fundamentals, and chemical principles forms the backbone of effective and safe wastewater treatment operations. Today, let's delve into some key aspects of sedimentation and flotation control. First, we'll talk about shock load management. Toxic waste shock loads can be quite challenging, but they can often be treated effectively with coagulants or chlorine. It's important to remember that any toxic solids generated should be disposed of in approved sanitary landfills, not in digesters or incinerators, to prevent further environmental issues. For smaller package plants that use activated sludge processes, adding lime to digestion units becomes crucial when the pH drops below 7. Maintaining proper pH levels helps sustain healthy biological activity, which is essential for effective treatment. Now, moving on to turbidity issues. When you see turbid effluent in small plants, it usually indicates that the return activated sludge pumping rate is out of balance. That imbalance can cause floating sludge that appears light-colored. To address this, reducing aeration rates can help eliminate that floating sludge and improve clarity. Finally, achieving proper sedimentation is all about careful monitoring, keeping an eye on flow rates, chemical dosing, and settling times. When these factors are managed well, you can achieve optimal clarification, which is vital for the overall efficiency of the treatment process. These controls are interconnected and essential for maintaining effective water treatment operations. Let's dive into the fundamentals of the activated sludge process, starting with frothing control. Frothing usually happens when the detention time in the reactor is too long. When this occurs, it can lead to excessive foam formation, which isn't desirable. To control frothing, we can use water sprays to break down foam, increase the dissolved oxygen levels to stabilize the bacteria, or waste solids more actively to reduce foam buildup. It's really important to get the detention time just right, because it directly impacts foaming and overall process stability. Next, we have settling tests. The goal here is to ensure we have the proper solids level in our settling tanks. In a typical 30-minute jar test, the ideal solids should settle to about half the depth of the jar. This indicates good settling characteristics. We also need to be mindful that solids should not stay in the settling compartment for more than 2 hours, as longer retention can lead to septicity, which causes unpleasant odors and process problems. Finally, let's look at oxidation ditch operations. When the mixed liquor appears dark gray, it suggests anaerobic bacteria are building up, which isn't ideal. Maintaining the dissolved oxygen between 1 and 3 mg/L is key to keeping the bacteria healthy and the process running smoothly. Overoxidation, on the other hand, can cause the floc to become very fine and pinpoint, which reduces settling performance. If you notice thick, dark foam, it's a sign that the wasting rate should be increased to remove excess biomass and keep the process balanced. All of these points highlight how critical proper control and monitoring are to ensure the activated sludge process functions efficiently and effectively. Now, let's take a closer look at some of the critical operating parameters for activated sludge. First, we have sludge production, which is measured in pounds of volatile matter produced per pound of BOD removed in a conventional activated sludge process. Typically, this ranges from about 10 to 15%. This tells us how much excess sludge is generated during treatment, and monitoring it helps us keep the process balanced. Next, there's the wasting rate changes. This refers to the maximum daily adjustment we can make to the waste-activated sludge rate to maintain process stability. Usually, this adjustment can be between 30 to 60%, allowing us to respond to fluctuations in load or process conditions without destabilizing the system. Then we have blower downtime, which is the amount of time the blower system can be shut off, say, for cleaning, without negatively impacting the process. In this case, about 5 minutes is generally acceptable, but longer periods could cause issues, so timing and planning are key. Finally, the sludge-age ratio, which is expressed in days and relates to the food-to-microorganism ratio, specifically, 1 pound of food per 5 pounds of organisms. This helps us control the biological activity and sludge age, ensuring optimal treatment. A few additional points to keep in mind. Air filter cleaning becomes necessary when the manometer pressure difference hits about 3 inches. Also, major storm events tend to decrease the percent of volatile matter in the aerator, and temperature fluctuations of around 10 degrees F, either up or down, can influence process efficiency. Understanding these parameters is essential for maintaining a stable and efficient activated sludge process. Let's talk about troubleshooting rising and floating sludge. First, what causes rising sludge? It's mainly due to septicity and denitrification processes. When sludge floats too early during a settleability test, it's often helpful to reduce the sludge age or increase the dissolved oxygen levels. Adjusting the food to microorganism ratio, or FM ratio, can also be effective here. Now, moving on to filamentous issues. These are a common culprit when you see floating sludge caused by filamentous organisms. To address this, you might want to increase the sludge return rate or reduce the mean cell residence time, known as MCRT. These filamentous organisms tend to thrive under low oxygen conditions or when the FM ratio is too low, so controlling those factors is key. Finally, let's look at some corrective actions. If you notice unequal MLSS concentrations between tanks, it's important to check for uneven flow distribution or possible blockages or broken diffusers. Also, keep a close eye on industrial discharges, as toxic loads can disrupt the microbial balance and cause issues like floating sludge. All these steps are part of a broader approach to maintaining healthy sludge settleability and overall system performance. Let's take a closer look at foam control and how process adjustments can help us manage it effectively. First, understanding the different types of foam and their causes is key. For example, dark tan foam often indicates that the MCRT, or mean cell residence time, is too long. To address this, we generally want to moderately increase sludge wasting to reduce that foam. On the other hand, if we see thick, sudsy foam, it usually means we have low MLSS, mixed liquor suspended solids. In this case, increasing the MCRT by decreasing wasting can help improve the situation. Now, pin flock resulting from toxic shock is a different scenario. To manage that, we want to get the sludge return rate as high as possible, which helps dilute and break down those flocks. White scum or froth often points to nocardia growth, which is associated with low dissolved oxygen levels or a low food-to-microorganism ratio. Moving on to organism indicators, certain microorganisms tell us a lot about the process conditions. For example, Sphaerotilus is associated with low dew or high FM ratio. When the FM ratio is high, you'll often see small mastigophora dominating the microbial community. If you observe old sludge with a high MCRT, rotifers tend to be present. Conversely, the presence of nematodes and predominant rotifers indicates a low FM ratio and a high MCRT. It's important to note that unless you're experiencing bulking or high SVI problems, you don't need to count filaments regularly. Overall, understanding these foam types and organism indicators helps us fine-tune our process controls, ensuring optimal treatment performance. Let's take a closer look at sequencing batch reactors, or SBRs, and what makes them a valuable option for wastewater treatment. First, they deliver superior effluent quality. This is because, during the final settling phase, the water remains motionless, which allows particles to settle more effectively. This results in cleaner water leaving the system compared to conventional treatment plants. Next, SBRs are capable of nutrient removal, including nitrogen and phosphorus, in addition to reducing BOD and suspended solids. To achieve this, we simply extend the reaction and settling times within the cycle, giving the biological processes more time to break down nutrients thoroughly. Now let's talk about the startup timeline. When starting up an SBR system, we typically seed it with sludge from another activated sludge plant, around 2,000 gallons, and it usually takes about 1 to 2 weeks for the system to become fully capable of effectively treating wastewater. And of course, aeration plays a crucial role here. Beyond just providing dissolved oxygen, it also helps mix the mixed liquor, promotes oxidation and reduction reactions, and supports the overall purification process. All these points highlight how SBRs are flexible and efficient, especially when aiming for high-quality effluent and nutrient removal, which are key themes in our overall treatment strategies. Let's take a closer look at advanced activated sludge operations, starting with return sludge control. In the nitrification stage, particularly with separate stage nitrification, the maximum return activated sludge rate is about 200%. This means we can recycle a significant portion of the sludge to maintain optimal biological activity. Using a constant percentage RAS control helps stabilize the food-to-microorganism ratio, or FM ratio, more effectively than just keeping the RAS flow rate constant, which can lead to greater variability. Moving on to nitrification requirements, at a temperature of 20 degrees Celsius, we generally need a solids retention time, or MCRT, of about 15 days to produce a fully nitrified effluent. It's also worth noting that most treatment plants typically lose less than 5% of total solids in their effluent, which is quite efficient. For successful nitrification, maintaining an optimal pH range of 7.5 to 8.5 is essential, and the temperature should be kept between 60 and 95 degrees Fahrenheit. Now, regarding respiration rates, these values give us insight into the health of our microbial community. If the respiration rate is less than 4 milligrams of oxygen per hour per gram of MLSS, that indicates the organisms might be stressed or unhealthy. Conversely, rates above 20 milligrams per hour suggest rapid biodegradation, which is usually a good sign of active biomass. Lastly, it's important to remember that the nitrogen demand correlates with the amount of volatile solids produced daily. Specifically, About 10% of the dry weight of those solids will require nitrogen for their biological processes. Connecting all these points, understanding and controlling these factors helps us optimize the nitrification process, ensuring efficient treatment and stable plant operation. Let's take a closer look at industrial and specialized waste treatment, starting with toxicity management. The most common cause of toxicity in these processes is detergents, which can be quite challenging to handle. On the other hand, chlorinated hydrocarbons are less common, but still important to monitor. When starting up an industrial waste treatment plant, we typically add chemicals until the mixed liquor suspended solids, or MLSS, approaches around 2,000 milligrams per liter. This helps establish a stable biological community. Now, for waste streams with highly variable flows, it's recommended to have a storage volume that accounts for about 25 to 33% of the total daily flow. Essentially, you store excess during high-flow periods and then release it during low-flow times, ensuring a steady treatment process. Switching gears to petroleum waste treatment, operating in extended aeration mode helps keep the food-to-microorganism ratio, or FM ratio, low. This encourages microorganisms to use sulfides as an energy source, which is beneficial for reducing odors and toxicity. If phenol levels in the effluent get close to NPDES limits, we can add hydrogen peroxide to help break down these compounds effectively. Lastly, phosphorus dosing is adjusted based on the mean cell residence time, or MCRT, and the concentration of total Kjeldahl nitrogen, or TKN, in the wastewater. This adjustment ensures optimal biological activity and efficient nutrient removal, which is key to maintaining a healthy treatment system overall. Now, let's talk about trickling filters and RBC systems. First, trickling filter operations. It's important to remember that food processing wastes often lack enough nitrogen and phosphorus, which are essential for biological treatment. Specifically, for every 100 pounds of incoming BOD, you need about 5 pounds of ammonia nitrogen to support microbial activity. One common nuisance insect we see here is the cycota fly, which can become a problem if conditions aren't managed properly. Moving on to chemical adjustments, chlorine is used to neutralize cyanide wastes, which is crucial for safety and compliance. If the pH goes above 9, acetic acid can be used to bring it back down. Conversely, if the pH drops below 6, sodium hydroxide, NaOH, can be added to increase it. And if you notice floating sludge, it's a sign to check the plant influent and make appropriate adjustments to optimize the process. Finally, let's discuss RBC maintenance. When nitrification is happening, it's vital to maintain alkalinity at about 7.1 times the influent ammonia levels. This helps ensure efficient nitrification. Also, if you hear excessive drive noise, that's often a sign of misalignment, which should be addressed immediately to prevent damage or process disruption. Throughout all this, it's clear that proper operation and maintenance are key to effective treatment, supporting the overall goal of sustainable and efficient wastewater management. Let's talk about waste treatment ponds management. First, the pH balance is crucial. When it gets too high, it can lead to anaerobic fermentation, which is not ideal. You might notice hard scum forming on the surface. That's a sign that anaerobic bacteria are thriving, and this often causes unpleasant odors. One of the main concerns with high pH levels is the development of blue-green algae, which can be problematic for water quality. Moving on to pest control, specifically chironomid midges. These pests require targeted pesticide treatments to keep their populations in check. However, not all nuisance organisms need chemical control. Some can be managed effectively by adjusting operational practices, like aeration or water flow, which can reduce their habitat suitability. Finally, let's look at aerator performance. Proper operation of surface aerators is key. When they're working well, you'll see very little foam on the surface, which indicates healthy conditions. If the pond appears gray rather than green, it suggests the pond might be overloaded or stressed. On the other hand, a light green color generally signals that the pond is in a healthy state with balanced biological activity. All these management practices tie back to the overall goal of maintaining a healthy, efficient waste treatment pond system that minimizes odors and nuisance organisms while promoting proper biological processes. Let's take a closer look at sludge digestion chemistry and how we can effectively control it. One important aspect is chemical neutralization. For example, when we add soda ash, it introduces fewer solids into the sour digesters compared to lime, which is a significant advantage. Plus, lime can sometimes cause dangerous vacuum conditions, so using sodium bicarbonate can be a safer and effective substitute. Additionally, biocatalysts, which are enzymes, play a key role in enhancing digestion processes. Now, moving on to beneficial concentration ranges. Maintaining ammonia-nitrogen levels between 50 and 200 milligrams per liter and magnesium levels within 100 to 200 milligrams per liter helps support optimal anaerobic digestion and methane production. These ranges are critical for keeping the process efficient. Finally, let's discuss supernatant quality issues. If the supernatant is of poor quality and causes plant upsets, it often indicates excessive mixing with not enough settling time. A sour odor suggests that the pH is too low, which can hinder the process. And if you notice foam, it usually points to too much gas recirculation. Recognizing these signs allows us to troubleshoot and maintain a healthy digestion process, ultimately supporting the overall efficiency and stability of our plant operations. Let's take a closer look at odor control technologies. First up, chemical treatment. Sodium hydroxide is a common chemical used to control sulfide generation. It works effectively at a pH of around 12.5 and can keep sulfides in check for a month or even longer. When using odor removal towers, it's important to remember the recommended organic loading rate, which is about 0.5 pounds of BOD per day per cubic yard of media. This helps ensure the system is working efficiently and not overwhelmed. Moving on to thermal combustion, this method involves burning odorous gases at very high temperatures. The optimal temperatures start at over 1,500 degrees Fahrenheit, which allows for more complete combustion of the odors. An added benefit of thermal systems is that activated carbon, often used in odor control, can be regenerated up to 3 times before it needs to be replaced. This makes it a cost-effective solution over time. Overall, both chemical and thermal treatments are vital tools in managing odors effectively, and choosing the right method depends on the specific circumstances of the site and the nature of the odors. Let's take a closer look at the process sequence involved in enhanced biological nutrient removal. It starts with a modified activated sludge system designed specifically for removing phosphorus and nitrogen. This system follows a sequence of tank environments: anaerobic, then anoxic, and finally aerobic. Each stage plays a crucial role in effectively removing nutrients from the wastewater. Moving on to ammonia conversion, one key step is raising the pH to between 10.5 and 11.5. This alkalinity shift encourages the conversion of ammonium ions, NH4+, into gaseous ammonia. NH3, this gaseous form is easier to strip from the water during treatment. Additionally, we use clinoptilolite in ion exchange processes, which is regenerated with salt, specifically NaCl, to maintain its effectiveness. Next, let's discuss the 4-stage Bardenfo process. In this setup, ammonia is oxidized to nitrate in the aerobic zone. It's important to note that the theoretical oxygen demand for this conversion is about 4.6 milligrams of oxygen per milligram of ammonia nitrogen. Also, the process typically operates with a mixed liquor retention time, or MCRT, of about 20 to 30 days to ensure proper treatment. Finally, in chemical phosphorus removal, the optimal pH range for adding ferric ions, Fe3, is between 4 and 6. Maintaining a low dissolved oxygen level, around 0.1 milligrams per liter, in the anaerobic selector is essential for phosphorus release. Be aware that filamentous bacteria, including Nocardia, can lead to persistent foaming issues, which we need to manage carefully to keep the process running smoothly. Together, these steps form a comprehensive approach to effectively remove nutrients biologically and chemically, supporting overall wastewater treatment goals. Let's start by discussing disinfection systems and safety. When it comes to chlorine chemistry, it's important to understand how hydrogen sulfide reacts with chlorine. Specifically, it takes about 8.5 parts of chlorine to 1 part of H2S to produce sulfuric acid. Also, if the pH drops below 5.5, you'll find dichloramine present, which can affect disinfection efficiency and safety. Now, regarding chlorine withdrawal from cylinders, if you're using 100 to 150-pound cylinders, the recommended amount is about 1 pound per degree Fahrenheit of ambient temperature. This helps prevent the chlorine from freezing, which could cause operational issues. Moving on to emergency response, it's crucial to know that our emergency repair kit C can stop leaks at tank car valves, but only at that specific point. If you observe liquid sulfonate or misting, that's usually a sign of a defective evaporator, and it requires immediate attention to prevent further issues. Lastly, to prevent the reliquefaction of sulfur dioxide gas, maintaining the room temperature between 80 and 90 degrees Fahrenheit in the piping area is essential. Keeping the temperature within this range helps avoid the formation of unwanted gas releases, ensuring safety and system integrity. All these points tie back to our overall goal of maintaining safe, effective disinfection processes while managing the chemistry and safety risks involved. Now, let's talk about some common issues with solids removal in the physical-chemical treatment process. First, small flock issues often arise when the paddle speed in the first flocculator is too slow, or if the baffling isn't set up properly. Changes in pH can also impact flock formation. To address these, we can try increasing the paddle speed, adding a coagulant aid, and conducting jar tests to verify the correct dosage. Moving on to large flock problems, these are usually caused by excessive dilution water, overly strong chemical makeup, or too much coagulant aid being used. The solutions involve optimizing where we add the coagulant aid, making sure it's in the right spot, and decreasing the paddle speed during rapid mixing to prevent oversized flocks. Floating sludge is another challenge, often caused by changes in the influent wastewater characteristics or malfunctioning cross-collectors. The best approach here is to perform jar tests, adjust chemical dosages accordingly, and inspect the scum collection devices to ensure they're working properly. Finally, operational checks are crucial. We should test the filter alarms every 60 days to ensure they're functioning, and after a proper backwash, the head loss should be around 0.5 feet. Also, keep an eye on media loss. More than 5 centimeters over 4 months indicates excessive where that needs addressing. All these points tie back to maintaining optimal solids removal and ensuring our treatment process runs smoothly and efficiently. Let's take a closer look at some of the residual solids dewatering technologies. First, vacuum filter recovery typically achieves a solids recovery rate of about 85 to 95% under normal operating conditions. This means most of the solids are effectively separated, but there's still some loss that we can aim to minimize. Next, sand bed recovery usually falls within the 95 to 99% range. This is particularly relevant for primary, secondary, and combined digested sludge on sand drying beds, where high recovery efficiency is crucial for optimal operation. When it comes to sand bed loading, a typical rate is around 10 to 35 pounds per year per square foot of dry sludge solids. Managing this loading rate helps ensure the beds aren't overloaded, which could compromise the dewatering process. Moving on to lime stabilization, an important point is that about 99% of fecal coliforms and streptococci are destroyed when sludge is stabilized with lime. This step is vital for pathogen reduction and safety. Additionally, lime curing or mixing generally takes about 30 minutes for effective stabilization. However, we might encounter issues with belt filter presses, such as polymer dosage problems, belt tension adjustments, or hydraulic loading concerns. These issues often require systematic troubleshooting to keep the process running smoothly. All these technologies and parameters tie back to our overall goal: efficient, safe, and sustainable solids management within wastewater treatment. Let's talk about the operational aspects of the multiple-hearth furnace. First, temperature management is crucial. The operating range typically falls between 1,500 and 1,700 degrees Fahrenheit. It's important to keep the shaft air temperature below 550 degrees to maintain proper conditions. Once the hearth reaches around 1,000 degrees, we can gradually increase the temperature by about 100 degrees per hour. The ideal burnout temperature increase is generally around 100 degrees per hearth, which helps ensure safe and efficient operation. Next, let's discuss the sludge feed requirements. The moisture content of the sludge should not exceed 75%. Proper feeding is essential, and the process of moving material inside the furnace is called rabbling. Ensuring the sludge is fed correctly helps promote efficient combustion and ash production, which is vital for the overall process. Finally, regarding flame characteristics, the appearance of the flame provides valuable clues about system balance. A bright, sharp flame usually indicates excess air, while a short, blue flame suggests that the excess air supply is adequate and properly balanced with the system. Achieving the right air balance is critical because it directly impacts combustion efficiency and overall furnace performance. So, keeping these key points in mind helps us operate the furnace safely, efficiently, and effectively within the overall system. Let's start by looking at atomic structure, which is fundamental to understanding chemistry. The first energy shell, often called the K shell, can hold a maximum of 2 electrons. This is important because when atoms transfer electrons, they form ionic compounds. So, ionic compounds develop through electron transfer, and it's worth noting that all replacement reactions are essentially redox reactions, involving oxidation and reduction processes. Also, when converting Celsius to Kelvin, we simply add 273, so 0 degrees Celsius equals 273 Kelvin. Moving on to acids and bases, all acids are polar covalent compounds, meaning they share electrons unevenly, which makes them polar. Some compounds are amphiprotic, meaning they can act either as proton donors or acceptors depending on the reaction. Basic anhydrides, which are oxides of metals, can react with water to form bases. Soluble metal oxides tend to cause alkalinity in water, so they can increase pH. In water chemistry, colloids are particles ranging from 1 to 100 nanometers, small enough to stay suspended but larger than molecules. Iron salt coagulants are effective at pH levels between 3.5 and 9, helping with water treatment. The water molecule itself has a covalent bond between hydrogen and oxygen. And Henry's law tells us that the amount of gas dissolved in water is directly proportional to the pressure of that gas at a constant temperature. That's key for understanding gas solubility. Finally, regarding hardness and its treatment, permanent hardness is caused by non-carbonate hardness, which doesn't easily remove with boiling. Zeolites, used for water softening, can be regenerated with sodium chloride. To remove ferrous iron, we use lime at pH levels of 9.4 or higher. For iron removal, pre-treating zeolites with manganese sulfate helps, and potassium permanganate is effective for manganese removal. All these concepts connect to overall water chemistry and treatment, helping us understand how to manage water quality effectively and safely.